What is this? Is this some kind of play on today's cipher type? I'm being kept a fixed distance from everything? Okay, there doesn't seem to be an official name for today's crypt type. One of the earliest examples of its use is in James DeMille's 1871 novel, The Cryptogram. One of the members of the American Cryptogram Association, link in the description, coined the name fixed distance for this type, and that's what I plan to use here. It's not particularly secure, but the principles employed for decryption are useful elsewhere. Let's meet in the training room. It may take me a while to get there. Encryption. The principle for encryption is simple. Just take the letter every n positions in the plain text. There are two variants. Take the letter and then count off n places, or count off n places and then take the letter. There is a restriction on n, though. If m is the length of the message, then n and m need to be relatively prime. Relatively prime here means that n and m don't share factors other than 1. Generally, this means that n and m can't both be even. This is a test message, is 18 letters long. Looking at potential values of n between 2 and 18, we can see that everything even shares 2 as a factor with 18. 3, 9, 15, and 18 have 3 in common. This leaves 5, 7, 11, 13, and 17 as possible step sizes. However, note that 1 and 17 act as mirror pairs. If n is equal to 1, we take every letter in order, T, H, I, S, and so on. 17 acts effectively as stepping minus 1, which just reverses the order of the string. Neither 1 or 17 are all that useful for creating ciphers, so we're down to 5, 7, 11, and 13 for this message. I'm going to switch to using E for our encryption step size. Picking 5 for E and using variant 1, we write T and then count 5 places. This takes us to the second S, which we record. Count 5 places to the third T and record that. Count 5 places to the second A, write that down. Count 2 places to the end of the string, wrap around back to the beginning, count the remaining 3 places to the first I, and continue this process until we get to the last letter. Group in 5s, and we're done. Our ciphertext is TSTAI, TEEIS, SHAMG, SES. Decryption. Decrypting fixed-distance ciphers requires understanding modular math, which is actually pretty simple. It's integer division, where we just keep the remainder. That is, if we divide 18 by 5, we get 3 with a remainder of 3. All we care about is keeping the remainder part. Therefore, 18 mod 5 is equal to 3, the remainder. The step size D for deciphering our crypt is given by E times D mod length equals 1. E is the step size we used for encryption. D will be our decryption step size, and length is our message length. We can also solve for E times D equals length times N plus 1, where N gives us different multiples of our message length. For our encrypted message, we used 5 and 18. So 5 times D mod 18 equals 1. For our test cipher, we can only use 5, 7, 11, and 13 for E, since those are the only values that don't share factors with 18. Notice too that E times D equals D times E. This becomes important in a minute. The smallest number we can have for E times D is 5 times 7 is equal to 35. And the largest is 11 times 13, which is equal to 143. So our multiplier N for the number of times we can wrap around our message for either encryption or decryption will range from 2 to 7. 18 times 2 plus 1 is 37. 18 times 3 plus 1 is 55. 18 times 8 plus 1 is equal to 145. Now 145 is bigger than 143, So we don't need n is equal to 8. We can just stop at n is equal to 7, 127. Just for the sake of completeness, let's multiply out each of the combinations for E and D and look at the totals. 5 times 7 is equal to 35. 5 times 11 is equal to 55. 5 times 13 is equal to 65. 7 times 11 is equal to 77. 7 times 13 is equal to 91. And 11 times 13 is equal to 143. Of this group, 5 times 11 is equal to 55 equals 18 times 3 plus 1. This means that if we encrypt our 18-letter long message with 5, that we decrypt with a step size of 11. We also have 7 times 13 is equal to 91, which equals 18 times 5 plus 1. This gives us our second pair of keys. So 5 pairs with 11, 7 pairs with 13, 11 pairs with 5, and 13 pairs with 7. And just for completeness' sake, 17 pairs with 17. As mentioned above, E times D is equal to D times E. Whichever of the pair is used for encryption, the other member decrypts the message. Taking the first letter and then every 11th, we get our plain text back. The second variation is to count first and then take the letter. Otherwise, the rules are the same. So we count to the second I, write that down. Count to the third S, write that down. Count to the second S in message, write that down. Wrap around to the beginning again, to H, write that down, and then continue. So the result is ISSHA, MGSES, TSTAI, TEE. And we're done. Omake, recovering K3 keywords. A second use of this fixed distance operation is in the process of recovering the keyword from what's called a K3 alphabet. One of the standards for making recreational cryptogram keyed alphabets was developed by the American Cryptogram Association, not a sponsor, link in the description, where the alphabets are identified as K1 through K4. Don't worry too much about the details. I'll talk more about simple substitution alphabets in a later video. Right now, we just need to know that K3 is one way to make a plain text ciphertext alphabet pair. With K3, we create a keyed alphabet as described in the basics video. Say the keyword is cipher. So we take cipher, remove any repeating letters, and append the rest of the alphabet. Then we use the keyed alphabet for both the plain and cipher alphabets. So we have cipher and the rest of the alphabet for both the plain and cipher lines. Finally, we shift one alphabet against the other. So we take the cipher alphabet and shift it 5 places to the left. Using K3, this is a test message would become YDAX, AX, J, YFXY, TFXXJNF. Usually, after the simple substitution crypt is solved, the letters are jumbled. Let's look at what happens if the alphabets look like this. It looks pretty random. The first step is called chaining. Here, we just pick a letter from the plain alphabet and write the matching cipher alphabet letter underneath it. So we'll take W, and W goes to M. Then we write that second letter on the first line and repeat. So next to W, we write M. M goes to F. We write F under M on the second line, and then we write F next to M on the first line, and we continue. Our final chained alphabets look like this. In fact, the lower alphabet is the same as the upper one, shifted one letter to the left. The next step is usually referred to as decimation, but you may recognize it as fixed distance transposition. The idea is to pick 3 or 4 low-frequency letters, such as W, X, Y, Z, or J, K, L, M, that we don't think are in the key. Looking at the top line, check if the distance between W and Y, or J and L, is the same as the distance between X and Z, or K and M. If they are, we can use them for setting the step size. Take that distance, divide by 2, and add 13. W and Y are 4 letters apart, as are X and Z. This is good. So we take our distance between W and Y, which is 4. We divide that by 2 to get 2, plus 13 is 15. Starting with whichever letter you like on the top row, write it down and pretend like you're decrypting a fixed distance cipher with D or E equal 15. Be sure to write the correct second row letters under those in the first row. Starting with W, write that down, count 15 letters to X, record that, count 15 letters to Y, record that, and repeat until you finish the reconstruction. W, 15 letters to X, 15 letters to Y, 15 letters to Z. Underneath we have MOVB. Shifting the 2 alphabets so that the upper one starts with the keyword, we get Asimov and then the rest of the alphabet. Beneath that, we're starting at C, continuing up to Z, we get Asimov, and then that's followed by B. And we're done. We can see that the keyword is Asimov. It appears in both lines, and the bottom line has been shifted 7 positions to the left. Returning to our E times D equation for our encryption and decryption step counts, 7 times 15 is equal to 105. 26 times 4 plus 1 is equal to 105. Alternatively, 7 times 15 mod 26 is equal to 1, which tells us that when we create a K3 alphabet pair, shifting the cipher alphabet relative to the plain text alphabet is just like encrypting it with a fixed distance transposition. And after the chaining step, decimation is identical to fixed distance decryption. There are a couple extra complications to K3, but we can leave them until later. If you want to try your hand at solving fixed distance, I pinned a few practice scripts in the comments below. If you want to see some methods for solving other types of ciphers, you can join the Black Chamber on Patreon to get access to the next video when it comes out, or wait until it goes public on YouTube sometime later. That's enough for now. See you at the next drop point. Maybe. Got questions, comments, or suggestions? Leave them in the comments below. Enjoyed this video? Then I encourage you to hit the like button and subscribe to this channel. If you want to show further support, you can join us over at the Black Chamber Patreon page, where you can get access to more how-to videos and PDFs on solving the cipher types covered here, additional crypts to solve, and more. Links pinned in the comments below. See you at the next drop point.